Okay, y'all ready for this?
Get up the ball.
Alright, when this all go over project.
Can I move?
Why?
He's messing with my stuff.
Sit right here. Go ahead. Right there. Okay. Quick review yesterday. What was work? Raise your hand. Carly? Okay, so it's basically using energy or converting energy to cause the physical system to change. Usually you need a force causing an object to move. Okay? Then we talked about what power was. What is power? What does rate mean? How fast? So basically power is how fast work is done. The faster the work is done, the more what you have? Power. The slower the work is done, the less power you have. Okay? So a more powerful engine will do more work over a smaller time frame. Okay. Then we talked about the 3 things needed for work to be done. I kind of put it on the board a second ago, but let's just quickly refresh again. What are they? Katie?
The force must be applied, the object must move, and the force must be applied to the object of motion.
In the what? Say that again, sorry.
Object in the direction of motion.
Yeah. Yep. Okay. What's the SI unit for work? What's the SI unit for power?
What?
Walk.
So I thought about making this a 1-day lesson. I'm going to break it down into 2. So we actually will have a part 3 tomorrow. Yep. This homework is still due tomorrow. I'm just saying I have broken the second part of this into 2.
Oh.
Earth to Sydney. So what was the heading of this chapter? Do you guys remember? Work and simple machines. Mechanical work is a big part of it, yeah. Okay? And we're going to talk about how simple machines affect work. What happened?
No, I don't.
What's wrong?
Nothing.
I don't have a...
You don't.
Carly, you need to tell him.
How about you do, Ethan?
Why don't you just tell me?
Yeah, tell me and I'll tell.
You have like a really long hair.
Oh, I did see that. Yeah.
Yeah.
Why don't you just say that? Not that big a deal.
Every time you're talking to be like, hello.
Guys, you can say whatever you want. I mean, well, within reason. But you can make fun of me however you want, as long as it's not like you're cussing at me or something. Okay? Time's up, I don't know.
I don't have the camera though.
Uh-huh.
Man.
We need to watch the one about Shane. The Shane story day.
You ever put that up?
That's up there, yeah.
It's not on YouTube. Shane is on YouTube.
Look, it's okay.
It went viral.
I can't see your face.
Shane's story. It's just called Shane's story.
Not one of my more defining moments.
Shane's story.
Well, actually a pretty defining moment. Not one of my more
Good device.
good defining moments. Yeah.
It's called Shane Sexy.
Die.
Oh.
Yeah, Shane went to it.
Shane was not very happy.
I didn't call him sexy.
Yes,
Yes, you did.
No, but
Yes, you
it was in the context of the story where the person who saw him
Are you
thought
saying
that.
he's not?
Oh, that's
Back me into a corner.
I know.
I'd rather not be.
Okay. Got this in? I'm not going to make the same mistake of putting that where I always put it. Spill it. stuff.
That was
On your
bad.
computer.
Like,
Mr. Kramer's
Should I tell you I spilled it all over the other day?
You spelled it again?
Yeah, but it didn't go all over my stuff. It was sitting right here. I spilled it. It got all over my pants.
Oh yeah, and then you keep it like on my pants, and I'm like, no.
Smart.
No.
Okay.
Don't get in trouble like that.
So, we are going to begin talking about the relationship between a simple machine and work. There is a purpose for using simple machines. Okay? There's a reason why it's in this chapter. Now, you guys are probably familiar with a lot of the simple machines. Who can name one of the simple machines? Lever, pulley, wheel and axle, inclined plane, wedge, okay? Elevator? No, that's... Okay? So, you're probably very familiar. Yes, we will talk about each of those individual simple machines, but we're not just going to do what you probably did in elementary school where you're like, hey, this is what this simple machine is. We're going to talk about how it relates to work.
Yeah.
I had it up my
We got your, oh wait, you had the, we got your right on
I had a couple people get hurt.
it? Oh, really? I have to look at that.
It was like right there. One person tried to like stand on it and swung.
Mr. Fincher got it at one time.
Mason Cole.
Oh.
That doesn't surprise you, that's what I said.
No.
Alright. So, what is the purpose of a simple machine?
Reduce the toil of work caused by the curse on fallen man.
Yes. So the purpose of a simple machine is so that I can either do work faster, it uses both, and do work easier. What does a simple machine not do? Change the amount of work. So you're probably thinking, if you're not changing the amount of work and you have the same amount of work whether you use a simple machine or not, how do we make it faster and how do we make it easier? And that's what the next couple days will be about. Okay? If I pull up the work equation, here's your work equation. Okay? If I had a, whoops, if I have this work equation, let's say the work doesn't change. So I have 20 joules of work. Okay? What would need to be true for the work to be easy? A big force to make the work easy? You want a small force in order for the work. For example, if I wanted to lift an object up into the back of a car, right? It takes a certain amount of force to lift up that object. Well, if I use a simple machine, I can actually reduce the amount of force I have to put on it. So the purpose of a simple machine is to decrease the force to make the work easier. Well, how do we decrease the force? Do what? Increase the distance. This is why we typically use a ram to get an object into a bed of a truck versus lifting it straight up. Okay? The more distance you travel, the less force you have to apply. Okay? And we will talk about that a lot more tomorrow when we talk about the distance principle. Okay? When we talk about levers and whatnot. But the thing you must know now is the purpose or the idea or reason for using simple machines is to what? Make work faster, make work easier. But what does it not do? Change the work. Same amount of work whether you use a simple machine or where you don't. So a simple machine just makes the work faster or easier, and we will talk about the distance principle in a couple days, probably tomorrow. Okay, here are a few. Here's where I know you guys mentioned like 5 or 6 of them, but all of the simple machines either fall under one of these 3 categories: either a lever, either a wheel and axle, or an inclined plane. Which one do you think a wedge falls under? Inclined plane. A wedge is a double-sided inclined plane. What do you think a screw falls under? A screw is an inclined plane. It's a spiral inclined plane. A spiral staircase is a screw. Does that make sense? Where do you think a pulley falls under? Wheel and axle. Okay. There you go. Make sense? All right. Oh, did you guys get that in? Sorry, did I go too fast? And again, we will take a separate day to go over one or two simple machines later when we start talking about once we get and have explained the distance principle, which that's probably the most important thing from this chapter is understanding the distance principle, which I'm pretty sure that comes tomorrow. Okay, we alluded to this last chapter. Yeah?
Yes.
No machine is 100% efficient. Is this anybody's? Yes.
So is the
No, it's not going to be a percentage.
So what's the unit?
It's unitless. It's a ratio. So if you have a joule divided by a joule, it's really just a ratio. So you could say it's a percent. That probably is fine. But I think of it as a ratio. So for example, we know that no machine is 100% efficient. Okay, yeah, this is probably best explained by a percent actually. Now, when we think of work in versus work out, think of it as energy, because we said work and energy were very closely related. Now we know that the energy that comes in is going to be more than the energy that comes out as far as usable energy, right? Because some of it gets lost in a form that we cannot what? Use. Okay? Is energy still conserved though? What do I mean when I say energy is conserved? Yeah, I didn't create or destroy, because if you think about it, if you just go, oh, well, more energy came in than went out, you would say, oh, didn't we destroy energy? Well, no, we just destroyed some of the usable, not destroyed, we just changed some of the usable energy into some unusable form. Amount of energy beginning and ending is always the same, it's just not always is all of it usable. Okay? So, when using this equation, I get students that ask me all the time, how do I know which is the work in and which one's the work out? Because you have to have a percentage that is what? Less than 100%. Okay, so what Stephen said was, is the energy in must be greater than the energy out, because mathematically that's the only way we're going to get a number that's less than 100%. Right? If I have a big number on top and a small number on bottom, I'm going to get a number that's much bigger than 100%. Make sense? Okay? So, maybe you want to write this down in your notes somewhere. You're always going to put the big number on bottom so that you will never have a machine that gives you more than 100% efficiency. So you don't have to worry about knowing the context of the problem and trying to understand based on how they worded the problem what goes on top and what goes on bottom. You should just know, oops, excuse me. You should just know we never have a 100% efficient machine. So if you plug in your numbers and you get over 100%, what do you probably need to do? Flip them. Okay? And let's do it. Cool?
Yeah.
For the Thunder? What? Who did they lose to now? Did they lose another game? No, you're just talking about the Portland game?
Yeah.
They needed to win that one. All right. Now, using that little principle that I just suggested, what is my work in? I can't hear you. 352. I'm just going to write it on the bottom here. Underneath. 352 joules of energy in. Okay? And we didn't destroy some energy. We just lost some energy into a different energy form that we could not use, so we didn't get quite as much work out as we put in. Multiply by 100, so yes, you do get your percent. What do you get? 93?
Yeah.
Did you do what I told you not to do? 93 point what? Now back in the day, that used to be really efficient. These days, that's not super efficient. We've gotten pretty good to be able to get the efficiency 96, 97, 98, but never 100. Okay. Questions on this? Everybody understand, when you're doing this problem, why the big number goes on bottom? All right, so the simple machines give us an advantage and introduce the mechanical advantage. What advantage do simple machines give us? Yeah. The advantage that simple machines give us is they allow us to do work easier and faster. Make it more simple. Okay. Never float your boat. What? Simpleness? Probably not. You just say it's simple. So what Carly said is absolutely spot on. Simple machines make work what? Easier and faster. What don't they do? Change the amount of work. Got the same amount of work regardless. They just make it easier and faster, and it'll make more sense when we talk about the distance principle tomorrow. We're just setting the foundation here. Okay? How much of an advantage it gives us depends upon some things in the simple machine. Okay? Which will make more sense when we talk about the distance principle tomorrow. The longer distance, the more advantage we have. Okay, and we'll talk about that, like I said, tomorrow. Okay, so if I have a mechanical advantage of 2, what does that mean? Any idea? If I have a mechanical advantage of 2, what does that mean? Reduced what by 2? Not the work. Why is it not the work? Because you cannot change the amount of work done. Oh, not power. What did we say? Yeah, the force, right? Okay? So if I say that the mechanical advantage is of 2, I would say that the work was 2 times easier. Or I had to apply half the force that I would have without a simple machine. Does that make sense? What if I said the mechanical advantage was 10? The work was 10 times easier. Or I only had to put in 1/10 of the force that I would have had to had I not used the simple machine. Okay? So if it takes 200 newtons of force to lift an object into some bed of a truck, and I use a simple machine that gave me an advantage of 10, how much force did I have to apply? 20. Right? 20 newtons times 10 times 10 gives me 200, right? So, if I have a simple machine that gives me a 10-fold advantage, I only have to put in 20 newtons of force instead of 200 newtons. Is that easier? What do simple machines do? Make work faster and easier. What don't they do?
Make it harder and more work.
Change the word. Yeah. Okay. All right. Yes. I don't think. Let me see. I don't think there's any. There might be one more. Nope. That's it. This is the last slide. This is just vocabulary for tomorrow when we start talking about the distance principle. We want to know what some of these words mean. Absolutely. Yes. Good question. As soon as you get this in, I can look. I don't have one printed currently. Do we have one? I don't know. I will find that out. Okay, I want to spend a little bit of time talking about this before you guys leave, because this is important vocabulary before we talk about the distance principle tomorrow. Okay, now I will bring this slide up. This will beginning of tomorrow, remind me to. But here's what this is. If I have a box that I need to lift, okay? That is what I need to move, right? I would call that box either my load or my resistance. Okay? Now stop. Listen. Okay? Resistance force would be the force I would need to lift the box without a simple machine. Does that make sense? So if the box weighs 200 newtons, don't I have to put in 200 newtons to lift it? Yes. That's the force that I would have to apply to get the box to move without a simple machine. Let's say I put a lever in here. Okay? So the effort force is the amount of force I would need to apply with the simple machine. And usually the effort force will be what? Less than the resistance force, because we know the purpose of a simple machine is to make it faster and easier. And wouldn't less force mean easier? Yes, you may leave. Never know. Let's go take it. Healthy Warriors? I think it's a good 7-game series. Am I going to be able to say dogmatically one team over the other? I think that's a complete bogus. You're just speculating, right? Well, unless it's a touch, I'd be okay with that. I would be okay with that. I would love to see a Thunder Warrior competition.